Welcome, ladies and gentlemen, to our next online lecture. This particular one is going to focus on the production of something called spectral lines. By the end of these notes, you should be able to generally explain how spectral lines are produced based on the arrangement of electrons in an atom. If you take a look at your notes packet, we're 6 pages in, and we are on the back of the 6th sheet of paper. So we're jumping around a little bit in terms of our order. We're making a little bit of an adjustment to kind of set the stage for some of the things we're going to do here before Thanksgiving break. Now, if we take a look, electrons and light are going to be able to have a lot of connections based on how the electrons behave. One of the things that we can identify for light is its spectrum. There is a range of colors in the visible spectrum. And if we take white light and pass it through a prism, it can be separated out into those different colors. What those colors represent are different amounts of energy. We see that the purple wavelengths of light correspond to high energy levels, and the red end of the spectrum correlates to low energy levels. What's happening is as electrons are moving around within their energy levels, as they fall back down to what we call a ground state, they're going to be able to emit energy. That energy can be emitted in different colors or different amounts of energy. So a continuous spectrum would represent when all kinds of electrons are jumping at all energy levels at once. So you don't see any distinctions between which are which. Now, for each individual element, it will have its own set of spectral lines that will be produced based on how the electrons move energy levels. What we see is that when an electron is excited, when we add energy to an atom, it causes them to move from the energy level they're in. An emission line would be what we see in our spectral lines. What energy amount is being emitted by an atom as those electrons fall back down to normal? Absorption would simply be the opposite. You can see in our examples here, emission is what it looks like when we have the energy coming out. Absorption is showing a lack of energy where that part is actually absorbed by the atom when we take a look at what goes past the sample. For each element, it's like a fingerprint. Each one will produce different emission lines because they all have different amounts of electrons within the atom. Now, if we think about hydrogen, the neutral hydrogen atom has 1 proton and 1 electron. So the benefit here is that we're going to be able to see specifically that electron moving around, and we can tie the results of these tests to that one single electron. We see part of a Bohr model of the hydrogen atom represented here on the right. What's happening is if you would heat or add energy to an atom, you're actually forcing the electrons further from the nucleus, or the higher energy levels. They always fill the lowest energy levels first, but if they have enough energy to move to the next level, they'll jump to that level. Now we know that the rings themselves, the orbits, were incorrect, but Bohr's idea about these energy levels comes from these emission spectral lines and the way that atoms absorb and release energy. So what we see here in the nucleus is our central location. N represents our energy level. And then we're going to be able to track that electron moving back and forth between these energy levels. Now, the energy levels are the possible locations of an electron relative to the nucleus. They will get further and further away the more energy that an electron has. Ground state for an atom means that all of its electrons are filling the lowest energy levels. This is the stable, normal condition of an atom. However, if we supply energy to the atom, we can cause it to move to an excited state. This means that some of the electrons have moved to outer energy levels because of that absorption of energy. This is an unstable state of being. It's going to have a tendency to return back to ground state fairly quickly because it's unstable. So ground state, all the electrons within an atom fill the lowest energy levels first. Excited state, I have some of those electrons that have been moved further from the nucleus because of an absorption of energy. Now, if you were to put a sample like this of an element into a flame, what you are doing is exciting the atom. You're causing those electrons to move to outer energy levels. As that energy gets released, when the atoms drop back down, you're going to see specific colors emitted depending on the element you've heated. The trick here is that that emission of light occurs when the electrons fall back down. So you had to put energy in to push them away from the nucleus, and then you have to see that emission once the electrons fall back down. The energy has to go somewhere. So as those electrons fall back down to their original ground state, the energy is emitted from the atom in these specific amounts or colors. So here we see some examples of emission spectra for several different elements. Remember that hydrogen, the advantage here, we can specifically tie these emission spectral lines to specific falls in energy levels. Remember, if this is an emission spectra, this is the energy that's released as an electron falls a certain number of energy levels. So the red line in hydrogen, right here, represents one energy level fall, small amount of energy. This one here, that's kind of a blue-green line, that is representing a fall of about 2 energy levels. Remember that I can't just stop these electrons in any random location. I'm either in one energy level or another. And the amount of energy it takes to get there is specific to the energy level it's moving to. So what we see with the hydrogen one, the further the electron falls, the more energy is released. Remember we said purple is a high energy color. Now, the more electrons an atom has, the more lines you can have produced, because we see more electrons moving around in the energy levels. The other thing to remember is just because we're only seeing, for example, here in the sodium, emission in the yellow range, there also can be emission lines outside the visible spectrum. So part of the emission of the energy from a sodium atom could be coming from other locations on the electromagnetic spectrum. So the biggest thing to remember, and this is our final slide for this one, is what we're really tracking when we see those emission lines are movements of the electrons between the energy levels within an atom. There are up to 7 where electrons can exist in an atom. The further the electron is from the nucleus, the more energy it has. Think of that attraction between the negative of the electrons and the positive in the nucleus. The electrons are being pulled towards the nucleus. The energy of the motion of the electrons is part of what's allowing it to exist that distance from the nucleus. The more energy the electron has in that movement, the further from the nucleus it can exist. So our next task when you come back to class is we're going to start exploring some of the locations of these electrons and how it correlates to the different spectral lines that elements produce. Your biggest thing to connect is the difference between ground state and excited state. When is the atom absorbing energy and when is energy being released? What's happening to the electrons when that occurs? Be sure in your notes packet to make sure that you summarize that in the appropriate location. There is a spot there where you can draw the picture in the right-hand column of this 7 energy level atom.